He is, as I said already, a professor at the University of Tokyo, working on fundamental aspects of statistical and quantum physics. He is best known as one of the initiators of the non-Hermitian quantum mechanics for his proposal of a model called the Hatano-Nelson model back in the 90s. Recently, he worked on non-hermiticity of open quantum systems and is delving into their non-Markovian dynamics. But today he will be talking about the error of time in quantum mechanics. So I'm very much looking forward to your talk. Please go ahead.
Thank you very much. Thank you very much for the introduction, and thank you very much for joining my talk. Do you hear me? Oh, back there? Okay. So before starting my talk, to just get a rough idea, how many of you are not familiar with quantum mechanics? Okay. How and the rest are basically familiar? How many of you hate quantum mechanics? I mean, that's okay, because if you, I'll talk about some equation of quantum mechanics, but if you don't understand, that's okay, because famous physicist Richard Feynman once said that if you claim you understand quantum mechanics, it's a proof that you don't understand quantum mechanics, okay? So we are just accustomed to quantum mechanics, right? So that's fine. Okay, so let me start my talk. So this is a collaboration with one of my friends, Gonzalo Ordonez in United States, originally from Ecuador. So this is him in this is in a museum. Is there someone from Czech? This is a museum of armor in the castle of Praha in Czech. And we visited Max Planck in Dresden and took a day tour to Praha. And this was from 10 years ago. And I went there, the Max Planck in Dresden, this year again, and this is my picture at the same place. Okay, so let me just introduce myself for couple of slides. So this is my CV. I took PhD in University of Tokyo. Perhaps if someone know Ryogo Kubo, he is a famous statistical physicist in Japan. I'm sort of an academic grandchild of him, and I'm proud of it. And and I worked on various topics, including not really a quantum mechanical system like quantum physics and something like that, but I'm best known by this work that I did back in 1996 when I was a postdoc in Harvard. I wrote this with David Nelson here, and this is probably the first paper that used the non-Hermitian quantum mechanics in the title. And we came up with some model. You don't need to care this details, but these red parts are the new part of the model, and it's named after our names. But you know, when I was a graduate student, I was taught that you should never call a model named after yourself by the name. Okay, so I would call it myself Nelson model, but of course you should replace myself with this. Okay, so this is my work. I work on from this on. I work on non-Hermitian quantum mechanics, particularly recently about open quantum system. Open quantum system is the system where, you know, there is a large Hermitian system, but inside it, if you focus only on a part of the large system, then it looks, you know, it exchanges energy between the environment, so it doesn't conserve energy or a particle number. So it's not a usual system you learn in university courses. So that's what I'm working on. And so okay, and today I'm gonna talk about a variation of open quantum systems, about arrow time. So what is arrow time? Arrow time is it's not about the direction of proceeding the time. It's the time is assumed to flow from the past to the future. But you see, when you as the time goes, you see more often something than the time reversal. For example, if you my apartment in OIST here is like this, very beautiful. But if I don't, do proper jobs, then half a year later it would be like this. Or I can show you a more a good example of arrow time. So you can see here that which is before and which is after, right? So you, as time goes, you see more often, things get broken, and we get older. So that's the problem arrow time. Why it's a problem from physical point of view? Because most of the basic physics laws of physics is time reversal symmetric. There's no distinction between the past and the future. So, but we see past and the future. So that's so how physics can explain that kind of phenomenon. So that's the big problem. So let me start with the Newton's equation motion. So this is m, and this is mass of the ball, for example, and this is acceleration, and this is the force. If the force contains magnetic field, actually it breaks the time reversal symmetry. But suppose it doesn't contain, then this is time reversal symmetric equation, because if you flip the sign of t, because there is the t squared here, the equation doesn't change, which means that the motion going into the future can be equally realized going into the past, right? So if you see this video, then you can tell that this video is going forward or going backward. Okay, so in this video you don't see any arrow of time, except that if you see the video for a very, very long time, then eventually you'll realize that this video was going forward or going backward, right? And so because the oscillation eventually diminishes. And why the oscillation diminishes here? Because, well, maybe if it's in a vacuum, then the oscillation keeps longer, right? I mean, there's always molecules of air would hit the ball, and that diminishes the motion of the ball. Or maybe this string is not really sturdy enough. It maybe oscillate too. Also, this sealing may not be strong enough. So that's how the balls oscillation of the balls diminish. So this tells you that the arrow of time appears because there are many degrees of freedom around the ball. Okay, so it's so this example tells you that we have to take many degrees of freedom just not just a ball. Okay, so that's why the problem of arrow of time is not really easy for physics. Okay. Okay, so this here is the quantum mechanics. This is the Schrödinger wave equation. It's about actually, this year is marked 100 year of quantum mechanics. It's invented, discovered almost 100 years ago. So this is the wave of matter. And this is the Hamiltonian. Now, you might think that it's not time reversal symmetry because this is here is T, just single T. But in quantum mechanics, actually time reversal symmetry involves complex conjugation too. So if you flip the sign T here and flip the sign of this I, then this differential equation stays the same. So also quantum mechanics, the role of quantum mechanics does not differentiate the motion to the future and the motion to the past. Okay, so there's no arrow of time there should not be arrow of time in this equation of motion, you think. But I'm going to tell you that actually it can be different in when the system is open. Okay, so that's how I'm going to tell you. So here is one example of arrow of time in quantum mechanics. Very simple problem. So you have two-level system. And here is the excited state. It's a ground state. This two-level system could emit the photon and goes down from the excited state to ground state, or it could absorb photon and goes up from the ground state to the excited state too. And but the thing is, there is an argument called Einstein's coefficients, and emission is actually divided by spontaneous emission and stimulated emission. So stimulated emission means that there are many photons, and then these photons would stimulate this to emit another photon. But spontaneous emission means that here is a vacuum, no photon here, but still this decays. And absorption rate is equal to the stimulated emission rate. And so there is always a spontaneous emission rate extra, and which makes this two-level system always decay, okay? Which is strange, which may sound strange because Schrödinger equation is time reversal symmetric. So that's what I'm going to solve today. Okay. Let's see. So this is it always decay, and the issue is because this is an open system. You see, two-level system is an open system. It's surrounded by large space with photons there. So if there is a mirror here, and two-level system has a mirror, is sandwiched with mirrors, then photons always back and goes and forth, and then actually it just oscillates, it never decays. Okay? If there is a leak of photons, then it decays, like this ball. Okay, so it's essential that the system is open when you have an arrow of time. Okay, so there are actually many types of arrows of time. Today I'm going to tell you is dynamic. I would say dynamic arrow of time, but actually when you see Stephen Hawking's brief history of time in chapter 9, he argued about the arrows of time. Actually, he doesn't have this dynamical arrow of time. He had these three arrow of time. So thermodynamic arrow of time, which means increasing of entropy. Okay, so like the apartment that I first said. Psychological arrow of time means we know the past, but we don't know the future. Okay, so that's the psychological arrow of time. And here's a cosmological arrow of time, which means that the universe is now expanding and not shrinking. And what he is arguing about in chapter 9 is, are the direction of these arrow of time just coincidental or not? For example, he argued, Stephen Hawking argued that when the universe in some distant future turns to shrink, then maybe the entropy starts to decrease. That's what he argued at one point. And maybe our our memory is inverted. That kind of argument he was making here. Okay, so it's quite an arrow of time. The emergence of arrow of time itself is interesting, but it's another interesting problem to solve is that are the direction of the arrow of time coincidental or not? So I'm going to talk about dynamical arrow of time, and eventually I'm linking this to the psychological arrow of time. So that's what I'm going to talk about. Okay, so I'm going to talk about the time reversal, breaking of time reversal symmetry. But there is in statistical physics, there is a famous symmetry breaking called spontaneous symmetry breaking. So this is it's called the Ising model. So Ising model is just an arrow which could point up or down, and it's a model of magnet. So each atom can have a small magnetic moment, and there is an interaction between them that try to align the arrows in the same direction. But when the temperature is high, then because of the temperature disturbance, they can't align together. So the free energy has only one minimum here. Okay, but when at the low temperatures, there could be there are two possible solutions. So one, mostly they are going pointing up, or mostly pointing down, and free energy has now two minima. And so this can happen only when the system is very, very large. Okay, so this is called spontaneous symmetry breaking, because nothing made the symmetry try to break the symmetry. They just break the symmetry. They wanted to break the symmetry themselves. Okay. Now the issue is here. Okay. So usually in statistical mechanics, they don't care which is actually realized. Usually when in the magnet, if you heat the magnet, then the magnet loses the magnetism. But if you cool down, then the magnet usually points whichever it wants. But it happens because of the small disturbance of Earth magnetism or whatever small disturbance in the environment. But usually you don't care which minimum is chosen. But in the problem of time reversal symmetry breaking, actually, I'm going to tell you now in the first part that there are actually two states that's sort of spontaneous symmetry breaking. Decaying state and growing state. The system has two time reversal symmetric decaying state and growing states. That's in physics, it's called resonance states and anti-resonance states. But the issue is you want to say that this is often chosen, right? Decaying, you want to prove that a decaying state is often chosen, and I'm going to tell you that in fact, if you consider the initial condition problem means that at time 0, you had this state. What would happen in the next? That's the initial condition problem. And I'm going to tell you that actually, if you consider the terminal condition problem, which means that at time t0, you have this state. What happened to make this state in the future, in the past? So that's the terminal condition problem. And if you chose the terminal condition problem, then actually you would choose the growing state, because you have to make it grow to this terminal condition, right? Okay, so that's what I'm going to tell you. Okay, and in fact, you might wonder how we could realize the terminal condition problem, and he did this. I'm not going into the details, but he realized by some data analysis that this is what you usually see when oscillation decays. Okay, but after reanalyzing the experimental data, he somehow generated how the things would grow into the terminal condition, and you'd indeed see that the decay oscillation grows into the future. Okay, so that's it's not really not unrealizable in experiments. The reason why I'm telling you so much about the arrow of time is there are currently many physicists just believe a very naive argument of arrow of time, which I don't like. It's the argument of recurrence time. Okay, so suppose you have two-level system again, and as I said, if you have a mirror, then the photon goes back and forth between mirror, and this two-level system emits photon but absorbs photon again, and it keeps oscillating. But if you make the mirror far and far apart, then this oscillation would become slower and slower, and eventually, so that's called the recurrence time. If you when it goes down and goes back to the excited state, it's called recurrence time. When you put the mirror far apart, then this recurrence time would get longer and longer, and you would only see this portion. Okay, so that's their argument. But you see, this argument does not tell you whether this is true or this is true. I mean, of course, we all know that initially the case, but I mean, it's just that we know this argument of recurrence time does not tell you logically whether this is the correct one or this is the correct one. Okay, so this is so I'm going to tell you now that the decaying state is actually connected to the initial state problem. Okay, from here, more quantum mechanics. So if you are not familiar, sorry about it. But in the quant element, so when I learned this kind of problem when I was in the third year in the university. So here is a quantum scatterer, maybe something, and then this is a quantum scattering problem. So you have, this is an incident wave. Incident wave comes to the scatterer, and some part of it is reflected. So this is a reflection wave. Some part is transmitted. Okay, and here's the transmission probability. Transmission probability is the ratio of the coefficient between the transmission wave and the incident wave. How much part of this incident wave is transmitted, and a square modulus is just how you need to do the calculation in quantum mechanics. Okay, and you typically see this kind of resonance peak. Resonance peak means that if you have an incident wave and incident wave scattered back and forth inside the scatterer, and after some time, it goes out. So that kind of resonance can, if that kind of resonance can happen, then you'll see this resonance peak transmission wave. Okay, and this is a typical form of resonance peak, and you see that if you this is energy, E is energy, so E must be real number in our real world. But if you you know, it's called analytical continuation in mathematics. If you make consider E as a complex number, then actually you find that this function diverges at here. And so there is a pole, and people soon realize that this pole is rather more important than resonance peak, because so this peak is just a tail of the divergence in the complex plane, and so what would happen here at the pole? At the pole, so this T is diverges here at the pole here, and which means that at this point the denominator of this coefficient is 0. Okay, so at this pole, this scattering problem, this incident wave must be 0. Okay, so at this pole, this incident wave is missing. This is the wave function at this pole. And in fact, already in 1939, I think Ziegert claimed that in quantum mechanics, you can find the resonance state by boundary conditions that you have only outgoing waves. Okay? So it's a bit strange. Nothing comes in, but something comes out. That sounds a bit strange, but if you solve it, then actually you can find such solutions. And these red dot. So this is the Schrödinger equation. Perhaps some of you don't like. And this is the wave number here. Okay, so this means that when x is positive, it goes to the positive direction. While x is negative, then it goes to the negative direction. So this means if Kn, real part of Kn is positive, then it indicates the outgoing waves. And in fact, for these red dots, a real part of Kn is positive. So these red dots are outgoing waves and called resonance state in physics. While in these green dots are actually for Kn, real part of Kn is negative. So it's actually incoming waves. And so it's called anti-resonance state in physics. Okay. Now, I'm going to tell you much about this equation, but so for resonance state, actually what's happening is, suppose you have some particles caught up in some potential wall, okay? And then in the resonance state, actually what happens is this particles that's caught up in the middle of the potential would leak out, and that gives you the outgoing waves. So that's the resonance state. While anti-resonance state, in the anti-resonance state, you put particles inside, and then the particles that caught would increase. That's the time reversal of the resonance state, and that's the anti-resonance state. Okay, and the important point is they are in fact computed as an eigenstate of the Schrödinger equation, which you usually don't learn in the quantum class of quantum mechanics, because it's about open quantum system. Okay, because resonance state is realized only when this goes out forever, right? If the system is finite, then this would hit the wall and comes back, and the resonance state would disappear. Okay, so you usually don't learn this in elementary quantum mechanics, but because it's really it must be open. It must happen only in open systems. Okay. I skipped most of the equation, but I hope indeed. So in the resonance state, this red dots, what happens is, let me show you again. It decays in time, and things go out. Okay, so it's a resonance state is actually a decaying state. And while anti-resonance state is actually growing state. So actually these red dots, resonance state is actually a decaying state, and these anti-resonance state, green dots, are growing state. And the issue is here. So as I told you, Schrödinger equation, original Schrödinger equation is time reversal symmetry. And but its solution can break the time reversal symmetry. So it's actually a difference. It involves this complex conjugation. I didn't tell you the details, but because of the complex conjugation in the time reversal reversal of the quantum mechanics, the solutions can break the time reversal symmetry, although the original equation is time reversal symmetric. Okay, and so that's what I want. I'm telling you here. And in fact, they always appear as a pair. So the whole system of solution still has the time reversal symmetry, but each decays in time. For example, let me just tell you this. So the time dependence of this state is given by this exponential to the minus I energy t, and in these red dots, this energy has a negative imaginary part. Okay, so if you insert the negative imaginary part, it means it decays in time, right? While these green dots, it has positive imaginary timing energy, which means it grows in time. Okay, so that's why these red dots are decaying states, and these green dots are growing state. But they always appear as a pair. So the whole solution still keeps the time reversal symmetry, but each solution can break the time reversal symmetry. Okay, so I've told you that when the system is large, very large, and there are no walls outside there, then you can have a decaying state and growing state. Now, the only thing I need to prove is that if you consider the initial condition problem, then actually this is dominant. While if you consider the terminal condition problem, then this becomes dominant. And actually, this is the most mathematically non-trivial part of my work, but I'm going to skip it. And this is how the survival probability looks like. Survival probability means this, okay? So suppose at time 0, you have this excited state, okay? So, this is the probability that after some time, at the other times, how much probability that this particle is still on the excited state. That's called survival probability. And indeed, as time goes, it decays like this, okay? But because of the total time reversal symmetry, for negativity, it grows, okay? Why does it grow? Because this is the terminal condition problem. If you want at time 0, if you want that it must be on the excited state at time z, what do you have to do in the past? What you have to do in the past is you have to insert photons and try to excite this two-level system to the excited state. So in the past, you have to make it grow. And in the future, it decays because it emits photons, okay? So this is the time reversal symmetry. And I can actually prove that indeed for positive time, this is mostly described by the decaying resonance state, while in the past, it's mostly described by anti-resonance state. So this is what I'm going to skip, but indeed, so that's how this terminal condition problem means. Okay, so it grows to this state from the past. Okay, this is a bit early, but I'm going to I'm coming to the conclusion. Okay, so I showed that the dynamical arrow time, you see always decay of this excited state is because you always consider initial condition problem. Okay, so if you consider the terminal condition problem, then you actually see growth. But you always see the decay, like people sliding the rails of the park, because you consider initial condition problem, right? Okay, so these guys, when you are at time t equals 0, these guys are on top of the rail, then you would see they are sliding down. But consider the terminal condition problem. At t equals 0, they were in the past, they were at the bottom of the rail, and at time, but t equals 0, they were on the top of the rail. Then they have to climb up the rail, right? So the reason why you see the decay in quantum mechanics is because you want to know the future. You don't because you think you already know the past. Okay, you want to know the future. That's why you always see decaying at least in the dynamical sense, in the quantum mechanics. Okay, so that's why I claim that this dynamical arrow of time you see always decay in quantum mechanics is actually related to the direction of the psychological arrow of time, that you want to always know the future. You think you already know the past. Okay, so that's my conclusion. And thank you for the time.
Thank you very much, Naomichi. Do we have any questions?
Yes.
Yeah. Please go ahead.
In black hole physics, we also have, it turns out that we also have a Schrödinger-like equation, which just comes from linearizing the Einstein field equations in a particular sense. And you get also resonant modes. But in black hole physics, we have a natural, the condition is naturally outgoing radiation conditions.
Right.
Because nothing comes out of the black hole, right? It escapes from infinity. So it's I would say a natural open quantum system, well, classical system, right? So we only have leaky boundary conditions.
So
I'm curious how you would translate that arrow of time, which we also don't really have in classical physics, what your interpretation of that is.
Okay, so the essential difference of this dynamical arrow of time, the thermodynamic arrow of time, or the classical system, macro system, is that it involves much more degrees of freedom than this quantum physics. What I told today is just spontaneous emission, which means that if you have a two-level system with the excited state, there are no photons. Okay, and if it goes down to the ground state, then it emits just one photon. Okay, so it's very, very simple. And in fact, I would expect that if experimenters try very, very hard, then you can actually realize the terminal condition problem, because I mean, if you see you observe the emission of the photon, and if you trace back the photon, then you would realize the actual terminal condition problem. So in quantum mechanics, that's I guess that's actually realizable. So, but in classical system, because it involves Avogadro number particles, degrees of freedom, it's actually very much different, these two. And indeed, as you said, it indeed seems quite impossible to, reverse everything, right? I mean, if you know how to reverse everything, then I mean, we can become younger. So there is a essential difference, and this is a much more difficult problem than what I talked today, and so I agree with you. I mean, it's I don't know how to I mean, as a physicist, I don't know how to talk much about the thermodynamic arrow time or classical.
Yeah, it's interesting though, because at least in this black hole scenario, that the equation's really reduced to a Schrödinger type equation. There's no, I mean, of course, a simplified setting, but
okay. Yeah,
it's as simple as your examples.
Oh, okay.
With a very specific potential, right?
Well, maybe you can tell me what the details of the problem.
Yeah, I'll talk to you after.
Okay.
Here was first. Yeah.
So, in the last plot that you showed, the direction of time decay. Surviving probability decaying. So in that, if you
this one,
yes,
okay,
wait for longer time, it will start grow, right? So
it will
the surviving probability will start grow because for the two-level system, because this initially it is at the excited state, it goes down and comes back.
No, because that's the point. If there is a mirror, then it hits back and comes back and it goes up again.
Yes.
And but here it's open till the end.
Okay.
So once the photon is emitted, then it goes away.
Yes.
And never comes. So that's why it decays and forever.
So practically, like whatever further the mirror is, but there is mirror somewhere. So if you wait for some time, for example, around the recurrence time, it will come back again.
I understand your question. Okay, in reality, it's not a mirror, but it's detector. So detector absorbs photons and never emits, at least in a coherent way. Okay, so if there is a mirror and a photon hits the mirror and comes back in a coherent way, then this is completely different. But if it's a detector and it absorbs photons, maybe it emits a photon, but in an incoherent way, then this is correct. Okay, so that's the big difference. Yeah.
Thank you for your talk. So can I summarize your conclusion as the time of arrow is derived from the dependence of the initial conditions? And, and for example, you say the Schrödinger equation is a time reversal equation, but its solution is not always the time reversal. Sometimes it's non-time reversal, but this is come from the dependence of the initial condition. And if the solution is time reversal, means it is independent of initial condition. What do you think?
Right. So the Schrödinger equation is okay. So let me summarize in the other ways. So the Schrödinger equation is time reversal symmetric equation, but as I said, it can have a time reversal breaking solution now, and I can prove that this decaying state is always dominant for after some state. If there is a necessary condition, okay? So the initial state must be time reversal symmetric state. If you start from the time reversal symmetric state, then it always decays. I can prove that. And if you consider a time reversal symmetric state and what happened in the past, then I can prove that this growing state always dominates. So that's the mathematical statement that I made.
So when the dependence of initial condition, if it is independent of initial condition, the solution is time reversible. So what?
Maybe I can't. I don't understand your precise question.
Maybe I should ask you later. Yeah.
Okay.
There are many other questions.
Yeah.
So I had maybe just clarification about the psychological arrow of time, I guess. So the way I understand it, at least I think is you said it in words earlier, is that like why we remember the past and not the future. Now, does this like symmetry of solutions or solutions that are both types? Does it?
So you are talking about this one?
The psychological one.
Psychological.
Yeah. So I'm wondering, like, because to me it's a kind of a question. Maybe other people know the answer. I just don't. Like, why do we remember the past and not the future? Like, why can't we see the future? Basically, like, what in physics causes memory to only function one way?
Right.
Do you think that connects to the thermodynamic arrow time, or is that, do you think, answered by the what we've done here?
So what I'm saying is that this dynamical arrow of time is the result of psychological arrow of time, but not vice versa. Okay. So for example, I could guess, for example, that suppose our brain takes advantage of increasing of entropy to memorize something.
Right.
Then we could maybe relate this thermodynamic arrow of time and psychological arrow of time. But so in that case, maybe psychological arrow of time is the result of thermodynamic arrow of time.
And do you have an opinion about that? Like, do you have an opinion about what the cause of the psychological arrow is?
Say it again.
Like, is that your opinion? Do you think that the psychological arrow of time is caused by the thermodynamic one or by?
Yeah, well, I mean, as a scientist, I can't say it's for sure, but possibly if we can prove say something like that, then that would be wonderful. I think. Yeah.
Got it. Okay. Thank you.
Yeah.
You mentioned this analogy to spontaneous symmetry breaking, and in the Ising model, you have something like a critical temperature, which distinguishes between the disordered phase and the ordered phase. What would be the temperature for this quantum example?
So, okay, that's I didn't tell you much about this, but there's there's no temperature, but this is the I think I should go back by here. Okay, so this is the wave number of this wave, and this is the real part of the wave number. This is the imaginary part of the wave number, and actually, this real axis of the wave number splits this whatever we usually see, and this time symmetry breaking solutions. So in the upper half plane, you will never see the time reversal breaking states, while in the lower half, you see the time reversal breaking states. And the reason is here it's these, if this is a pure positive pure imaginary, if you insert this positive pure imaginary, then actually this function looks like this Mount Fuji. But if you insert this negative imaginary parts, then actually it diverges. So it's not a usual function. It's diverges for in the infinity. That's because particles goes away into the infinity. So these states are not really normalizable functions, and that's actually directly related to the fact that it can break the time reversal symmetry. Okay. So this upper half plane and this lower half plane of the wave number is the actual difference, something like critical temperature.
Okay, I see no more questions. So if you want to find Naomichi, you can come upstairs to the visiting program area. We also have a coffee time tomorrow with the visitors. So if you want to have a chat, please come by. And otherwise, let's thank him very much again for his nice talk.
Thank you very much. Thank you.